So in an earlier example, we looked at calculating your mortgage based on the interest rate and how much extra principal you were paying, and you could play with the numbers and see how the calculation changed. You could do a lot of things like that with spreadsheets. So let's look at another example, and in this case, instead of dealing with financials, let's deal with the world of physics. And let's say we want to trace a projectile as it moves. You know, you fire it out of a cannon, how high is it, how far does it go, that kind of thing. Typical problem you might find on a high school physics test. So let's get rid of the header column here, and let's add 3 columns. First will be the force. So this is the force that the projectile or cannonball or whatever is fired out at, and then the angle we'll do it in degrees, and then gravity, which is in meters per second or meters per second squared. And let's bring that down to just those. These are just going to be settings. There's just going to be one value for each. So we're going to select this and shrink this table all the way up. And we'll say that the force, initial force in meters per second is going to be 100 meters per second. And the angle in degrees is going to be a 45-degree angle. And gravity is going to be 9.8 meters per second squared. And let's call these the parameters there. Now let's create another table. And this table is going to show the progress over time of the cannonballs. So we'll do a table, do this kind of table, have it underneath. And first there'll be time, and then speed horizontally, speed vertically, the position horizontally, and the position vertically. And we'll start with time of 0. Now we want to calculate the initial speed. The initial speed horizontally is going to use a function from trigonometry, the cosine. You might remember this. You break apart a vector like 100 meters per second at 45 degrees into horizontal and vertical components. Cosine is the horizontal component, and sine is the vertical one. So the formula here would be to take the initial force, and we're going to make sure that's absolute, because this first time here, time 0, we're going to preserve row and column, so it only looks at the cell. And then we are going to multiply that by the cosine of this angle. Now the cosine function takes radians, but we've specified degrees. Fortunately, there's a way to convert. So the radians function, you can see here, converts degrees to radians. So we'll take this here, and again I'll make sure it's absolute, and put the parentheses after that. There we go. And now we get this horizontal speed. Very nice. I can copy and paste that, and for the vertical speed all I need to do is change cosine to sine. And now we'll get the vertical speed. Since it's at a 45-degree angle, these are equal. So it's basically traveling as much horizontally as it is vertically. It's being fired up at a 45-degree angle. We could test that by saying, okay, what if it was fired at a 60-degree angle? And we could see now that the vertical speed is greater than the horizontal speed because it's firing more upwards than it is horizontally. So let's go back to 45. Position horizontal and vertical, well, this is time 0. We're starting at 0, 0, the initial point. So that's where we're at. At time 0, it hasn't moved at all. It does have an initial speed, but there's been no time for it to actually apply that speed to change its position. So now we go to the next row, and the time is now moved forward 1 second. So what's going to happen to our horizontal speed? Well, horizontal speed is not going to change at all. We're not taking into account friction or air resistance or anything like that, so the horizontal speed will remain the same. So we could copy and paste this in here and get that. Now the vertical speed will also stay the same, except we have to take into account gravity. Every second that goes by, 9.8 meters per second is removed from the speed. So we will go and create a formula equals, and we'll take the previous second's speed and subtract gravity. So gravity is going to pull down. The cannonball is being fired up, but gravity is going to pull down. And we're going to make sure that this is an absolute value. So it's always referring to 9.8. And we could see here in the second here, it is going to be moving slower. It's still going to be going up, but not as fast. Now, position is going to change. So what we want to do is we want to take the previous position and add to it the previous horizontal speed. And same thing here. We want to take the previous vertical position and add to it the previous vertical speed. So it's referring to the column above it. So at time 0, it is moving that much. So at time 1, it actually gets that far. Now what's going to happen for time 2? So we will enter 2 in here, and we will copy these and paste them in. And we'll see the horizontal speed is unchanged. The vertical speed has slowed down. It's not moving as quickly upwards as it was before. The horizontal position has moved the same amount, and the vertical position has moved up, but not as much because it's slowing down. It's only moving here at 60 meters up rather than 70 meters up. So let's condense this here, and now we will add another row. I could hit return here, add the time in, return again, continue to add that time in there. I could make this a little easier by saying this is equal to this plus 1. That's the way I like to do it. So now I can copy this and paste it in here. So now every time I add a new row, it automatically increases the seconds by 1. And you could see here the horizontal position changing, the vertical position changing, the speed changing. When we get to one point here, the speed now becomes negative. Gravity has now stopped the cannonball from moving upwards at all, and now the cannonball is falling back towards the ground, and it's going to fall towards the ground faster and faster. So what happens if we keep adding rows? Just drag down here, it's going to add more. Notice at one point the vertical position changes to negative. So what happened here is it started at 0, went up to 70, 131, 182, kept getting higher and higher, and then here you could see the vertical speed went from positive moving up to negative moving down as gravity took over, and then the vertical position started to go down, down, down until it went negative. Negative would represent that it's below ground. So obviously it's going to hit the ground and not go below ground. We can select that column there, go to cell and conditional highlighting and add a rule and say if it is less than 0, then make it red. And you can see now clearly where it would keep going down if the ground wasn't in the way. So let's clean this up a bit. We don't need all this space here for time. We can shrink that down quite a bit. We can also go in and change these columns so the numbers there don't have all these decimal places. Since these are estimates anyway, going second to second, we can go and say that let's have data format of a number with no decimals. And we can shrink this down like that, so it's a little bit easier. We can do a title over time here. So now we have some interesting data. What would be nice is to visualize it. And we can do a visualization pretty easily using a scatter chart. The horizontal and vertical positions, if we plot those on a scatter chart, this is what we get. We go to chart and we do scatter, and we get this. Each point is placed here at its horizontal position and vertical position. So here's 0, 0, and that's the first one. Then here's 71, 71. So each one is plotted, and we look at that. we see the path of the cannonball. And we see here it goes below 0. So we may want to remove that at this point and get rid of these two. Right here I can select them. I can say delete the selected rows. The chart here will automatically update. Now we can see the path of the cannonball represented in a scatter chart. So the great thing is we can update these initial parameters because that's all we have control over. We could say, what if there's a little bit more force? What if instead of 100, it's 110? And watch what happens. All these numbers update here, and so does the chart here. So you could see it actually moved. It's moving further because we're firing it a higher amount. Now, it was hard to see here. These numbers change as well. It went from 0 to 400. It goes 0 to 400 now, but if I did 100, it goes to 0 to 300. So what might be useful is that get this fixed so it's not actually going to change to adjust. So I can go and change the axis here and say, so for the x-axis, it's going to 1200 now. Let's say it's going to go to 2000 and 0 will be that. And let's say for the y-axis it'll also start at 0 and we'll do a maximum of something more like say 1000. Okay, so we've got that there. One of the nice things about this is we can expand this here again. And now it goes below the ground, but because that can't be represented on the chart, it's not there. But that's fine because if we're going to change these numbers, so we change to 110, now it'll show more because it'll go a little bit further. Well, actually it'll go the same distance. If we change the angle, like let's say have it go up more, or we can have it go that way more. We can do lots of different things. And it won't matter. You know, in this case, firing at a force of 200 is going to change how long it's in the air. So we had the extra rows there. And this changed to show us what was going on. Go back to 45 degrees at that. And we can adjust this if we need to. We definitely need this to be bigger if we're going to be using forces like that. But let's go back to like 125. And we could see that. And what if we did 75-degree angle like that? Here we actually do run out of rows. Let's add more. Now we can see the complete path. So, you know, if you're trying to hit a target like right here, right at 1500, you could try to figure this out. You could try to figure out, okay, 1500, that's too much. Let's reduce the force a bit. And maybe just a little bit more. There we go. Bullseye. We hit right there just by adjusting the force and the angle of the cannon. We could also go into this chart here, into the series itself, and say that we want connection lines to connect them. And not only will it connect the existing circles here, but the ones that are even beyond the edge of the chart. So we can see exactly where it goes. And we can even get rid of the data symbols there and just see a line. So we can now get a really good idea of what is going on. And it looks even better. We could go and change the axis here so we could see, for instance, right here, the x-axis, we can have a name shown. And we can do the same for the y-axis. We can do a name. So we can change these now. We can say altitude. And we could say distance. There. So we can play around with this a lot more. Probably get rid of this here. Make the chart look better. Change the colors. Adjust the grid lines and things that are used here, whether or not you want them or not. And come up with a chart that works really well and goes with the data and what you're trying to do.